So these are the three aromatic compounds. If we just see according to the Kale's rule, these are the fully conjugated systems. These all molecules are planar, cyclic, and contains 4n plus 2 pi electrons. So how? So here 4 into 1 plus 2 is equal to 6 pi electrons. Here this contains 4 into 2 plus 2, that is equal to 10 pi electrons, and here it is 4 into 3 plus 2, that is equal to 14 pi electrons. So according to the Kale's rule, as these molecules are planar, means all the carbons and hydrogens which are present in these molecules are lying in one plane, and so these molecules are planar, cyclic, fully conjugated system, and so they obey the Kale's rule. And so as they obey the Kale's rules, they are termed to be the aromatic. And so in this way, the aromaticity of these aromatic compounds is described. Now, whenever this molecule was being studied, benzene, it was being studied since 1825. Then in 1865, August Kale, he has explained the structure for the benzene, and so the structure of benzene and the stability of benzene, structure and stability of benzene. So any compound which resembles with the properties of the chemical behaviors of benzene were termed to be aromatic, and then the different structures were being studied, that is the Diva structures, Kale structures, or Kale structure. So Kale explained the structure of benzene in this way. Diva structure of benzene was in this way, and Kale structure was in this way. So these structures were identified by studying the different types of properties of the molecules, and when the structure of August Kale's structure, when was considered for the further studies, it was studied. It shows the low heat of combustion and low heat of hydrogenation. Means by carrying out the hydrogenation reactions in the combustion of the molecules, the energies which were calculated were found to be very low. Then the structure of August Kale's, that is the three structures and Kale structure, were identified, and so these structures are similar or same. So these are the two August Kale structures, and this is the Kale structure. And so after considering this, and this were confirmed by the stability of benzene. Why benzene gets the stability? So benzene is a molecule in which there is a presence of 6 carbons and 6 hydrogens, and all these carbons which are present in this are sp2 hybridized. They are all sp2 hybridized, and when it's a sp2 hybridized, the structure is trigonal planar. So the structure of this carbon, it will be like this. So, and there is the presence of one unhybrid p orbital. So in this way, if you just draw the structure of benzene, you will see that these are the 6 carbons at the 6 corners. Here it contains, this is one sigma bond or one lobe which forms a sigma bond. Here this is the another lobe which forms a sigma bond. Means in this way, if here we will consider that this is in this way and this. So the two hybrid loops are involved in the carbon-carbon single bond formation, and one hybrid loop is involved in the carbon-hydrogen bond formation. And so in this way, all these 6 carbon atoms here, they are forming the sigma bonds with each other by using 2 loops, one of each. This is also having one hybrid loop, this is also having one hybrid loop. The one hybrid loop is available for the hydrogen bonding. So in this way, here we are getting the formation of the 6 carbon hydrogen bonds, and in each bond there is one carbon carbon sigma bond. So all these are the sigma bonds, means 6 carbon carbon sigma bonds and 6 carbon hydrogen sigma bonds. And one unhybrid orbital is left with each carbon. And so this undergoes lateral overlap and forms 3 double bonds. This undergoes the lateral overlap. Sigma bonds are formed by the axial overlap, and the pi bond is formed by the lateral overlap. And so in this way, this lateral overlap is taking place in between the unhybrid orbitals of the carbons. And so, if these are at the same distance, means this, if this overlap is possible, this overlap is also possible. And so, in this way, this overlap can also become possible. And so, here we are getting a continuous pi electron density above the plane and pi electron density below the plane of benzene plane. And so, this is called as the continuous delocalization of the pi electrons. This is called as the continuous delocalization of the pi electrons. And so, due to this continuous delocalization of the pi electrons, all the carbon-carbon bonds cannot be considered as single or double immediately. So, both the bonds are showing the uniform bond length, that is 1.39 angstroms. 1.39 angstroms. And so, in this way, this gives a special stability to this molecule, aromatic molecules. And so, here we get or we confirm the structures of the benzene in this way. So, we draw the structures of benzene either in this way, or we draw the structure in the another way by changing the positions of the double bonds, or we can say, so with this both the structures are same, and then in short we can show a circle in this ring which indicates that there is a continuous delocalization of the pi electrons in this system. And so in this way it acquires a special stability. And as we discussed, that when the benzene molecule tends to give substitution reaction rather than addition reaction, if it gives addition reaction, the one double bond is getting converted into a single bond. Means the two substituted molecules atoms are getting attached to the two adjacent carbon atoms, and so this aromatic character of the benzene is lost. And so when the aromatic character of the benzene is lost, we are not getting the aromatic character. We are not getting the aromatic character. And so further, in this way, this molecule acquires the stability, and these are the structures of your benzene molecule. And now, now we will further go for the nomenclature system. Nomenclature system. And so, the nomenclature of these compounds can be done on the basis of IUPAC nomenclature system, that is the International Union of Pure and Applied Chemistry. So, whenever it's a single molecule, that is benzene, we call it as benzene only. But when there is any substituent or when the hydrogen atom of this benzene is getting replaced by any other atom, suppose it is chlorine, it is termed as chlorobenzene. When it is a bromine, it is called as bromobenzene. When there is a presence of a nitro group, it is termed as your nitrobenzene. And so in this way, these are the derivatives, or these are the examples of some monosubstituted derivatives. And some monosubstituted derivatives are having the, means here the prefixes of the substituents are added before the name of benzene. The prefixes, that is chlorobenzene, bromobenzene. So the chloro, bromo, iodo, nitro, these are the prefixes, means that comes before the word benzene. Then some of the molecules are having the common names. So this, according to our system, a simple nomenclature system, we will call it as methylbenzene, because the methyl comes, is the prefix of a substitute which comes methylbenzene. But there is a common name for this molecule. It is termed as toluene. It is termed as toluene. Then the second example for this, that is hydroxybenzene, but it is often called as phenol. It's often called as phenol. Then this is your aniline. The common name of this molecule is aniline. But if the, according to the nomenclature system, the common nomenclature system, we can call this molecule as hydroxybenzene. This can be called as a aminobenzene. So some common names are also used. Then, if there is a presence of the two different types of substituents in a molecule with two different substituents. Now in this, there are different kinds of molecules. If both the substituents are same and they are attached in this way, so here there are three different examples. So how we will give the names to these compounds? So when the substituents are at a different positions, so with respect to the any one substituent, means in a monosubstituted benzene, when there is any one of the group in the molecule that takes from this position, the positions adjacent to this substituent are termed as ortho, which are at the second adjacent position, they are termed as meta, and when it is exactly opposite to the substituent, this position is termed as para. And so for this, the abbreviations, that is O, M or P is used. And so in this way, in the common nomenclature system, we can call these molecules as ortho-bromo, ortho-dibromobenzene. So the prefix, this di indicates the two substituents, and both the substituents are of bromine atom. So ortho-dibromo, they are adjacent to each other. So it is termed as ortho-dibromobenzene. These are meta to each other, and so this is termed as meta-dibromobenzene, and this is termed as your para-dibromobenzene. And so in this way, when these substituents are same, you can use this, or by IUPAC nomenclature system, it is assigned as 1, 2, 3, 4, 5 or 6 positions. So you can call this molecule as 1,2-dibromobenzene, 1,3-dibromobenzene and 1,4-dibromobenzene. So both the systems can be used, the IUPAC nomenclature system or the common nomenclature system. So whenever it becomes difficult to give the name, we are oftenly using the IUPAC nomenclature system because it's easy. Then further we can see that the substituents are different. If the substituents are different, so here if we say chloro, so when it is chloro, it is orthochlorobromobenzene. Orthochlorobromobenzene. Here metanitrobenzene. Metanitrobenzene. Here we can say parabromophenol. It's called as a parabromophenol because here this phenols and this is at fourth position 1, 2, 3 and 4. So it will be termed as your parabromophenol or it is 4-bromophenol. 4-bromophenol. It can be also termed as 4-bromophenol. Para-dinitrobenzene, or you can say 1,4-dinitrobenzene. 1,4-dinitrobenzene. And if you just write it in this way, or if the substituent is changed, so here it is orthonitrotoluene. And so while giving the names, you can use this system of nomenclature for giving the names to any different types of substituents. If there are 3 substituents at a time, it's 1, 2, 4. 1, 2, 4. Tri-bromo. Tri indicates the presence of 3 same groups. Tribromobenzene. Tribromobenzene. 1, 2, 4. Tribromobenzene. Then so this is a molecule in which the 3 substituents are totally different. So you will say here 2-chloro, 4-nitrophenol. 2-chloro, 4-nitrophenol. So this is the way in which we can give the names to the different types of compounds. The nomenclature system can be studied thoroughly. And if there are more number of substituents, that is 1, 2, 4, 5, 2, 4, 5 trichloroaniline, 2, 4, 5 trichloroaniline, or you can say here another molecule. So here this in short is called as PNT, that is trinitrotoluene. Trinitrotoluene. So in this way the nomenclature system is carried out or gets studied. And so, if ever you are having any problem, we can just go to the different types of references, or we can contact to the teachers whenever it is necessary. Okay, thank you very much. So we will continue in the next lecture.